Hi, this is Professor Stugard, and in this lecture we're going to be discussing data types and data structures. So our goals for this video, we want to make sure that we understand the main ways that data are stored on our computers. I also want to focus on learning the difference between a list and a vector in some of our other data structures. And also I want to make sure that we're able to check what our data types are in the R programming language. So before we really get started, let's get a few definitions out of the way first. So when we have data types, a data type really is just a reserved memory location to store values, which are also sometimes called literals. And when we use the word literal, that is our assigned value. So for example, if I had name, and inside name I wanted to store the value Joe, in quotation marks, name is my variable, and then Joe is my literal. So the literal value that's inside my variable is, well, my literal in that case. And then of course my variable is my variable name, however I've declared it. So when we talk about data types in R, there are 6 basic data types. We're going to learn about 5 of these. We're going to learn about characters, which are like names. We're going to learn about numerics, which are our real numbers or our decimal numbers. Integers, which need to be whole numbers only. Our logicals, which are just true and false. Complex, which again is outside the scope of this class, but we might as well mention it. Now, the last data type that we're not really going to talk about is raw data. And in this case, when we say raw data, we're talking about data that is stored basically one step up from binary. One step up from the zeros and ones, and not in a really useful way for humans to interpret. Then we're also going to discuss our different types of data structures. And so our data structures are how we combine different data types to form some sort of cohesive structure for the data. Now there's many data structures, but we're going to focus on 5. So we're going to focus on vectors, and in particular we're going to focus on what are called atomic vectors. Vectors that only have one type of data type. So either everything in that vector is, say, a character, or everything in that vector is a numeric. They have to be just one type. Then lists, factors, data frames, which we've been working with, and matrices. So we'll start off with the characters, and so the character data type stores our string of letters, numbers, and symbols, and we explicitly store the character data type by enclosing that string in our quotation marks. So for example, if I have the variable x, I can store Tungus Community College, all in quotes, and it's going to store it exactly the way I've written it, with the spaces and the uppercase, lowercase all mattering, and it's going to preserve that entire thing. I can also, in my characters, in my strings, I can also obviously put numbers and symbols, so like the subject code MAT*167, I can easily store that as well, and I'll be able to recall that later. Now, it's really important to recognize when things are being stored as characters, because numbers can be stored as characters, and when this happens, we're not going to be able to perform arithmetic with it. All right, so for example, let's say I have my variable x, and I want to store 6 in there. Now, if I put the quotes around 6, it's going to store 6 as a character, which means it's not storing the numerical idea of the quantity 6, it's just storing, almost when I think about it, like the picture of the number 6. It doesn't have any numerical meaning, it's just a random character that shows up on your keyboard. That's all it's going to interpret this as. And that's because, well, there's quotes around it. And anytime we use quotes, it's automatically going to store it as a character, even if it seems like a number. So what's going to happen if I accidentally store my numbers as characters? So let's say I store another number as a character. In this case, let's say I try to store 2 in my variable y, but again I use quotes, which makes it a character. If I try to perform the operation and add x plus y, well, I'm going to get an error. And luckily this error is pretty explanatory. I get an error in x plus y. We have a non-numeric argument to a binary operator. Basically, it's telling me that my x and y are not numbers, so I can't add them together. How would I possibly add letters together, right? How could I add or names together or strings together? Like in the last example, how could I add Tungus Community College plus MAT*167? It doesn't make sense. Our next data type are the numeric data types. And so numeric data types store the majority of our numbers. This is also sometimes referred to as a double, and we actually will have it called a double when we run our code in R. This basically includes all of our real numbers or our decimal numbers. So, for example, if I have the variable x and I store the literal 2.17, I can use type of function, and it's going to determine the data type of, well, my variable. And so in this case, if I use that function type of, and I say type of x because that's my variable I'm looking at, the type of x is going to show up as double. And again, double means a numeric value that can, well, basically store decimals for us. Now, we want to be really, really careful with our doubles and our numeric values because computers use what's called floating point arithmetic to store values. Floating point meaning the floating decimal point, which this can lead to some rounding errors, which can lead to your code not working as you would expect it to work. So, for example, if I had the two fractions 7 over 13 minus 3 over 31, if I actually subtracted them and I did it out by hand and I found the common denominator, which is 403, and subtracted them, well, it's going to give me the result 178 over 403. And that is the exact value. Now, however, if I tried to run this in R and I subtracted those two fractions in R and I stored that value in X, so if I subtracted 7 over 13 minus 3 over 31 and I store that in my variable X, if I check, does X equal the value 178 over 403? And again, remember when we use mathematical operators and we're checking whether they are equal, we have to use the equals equals, the double equals here. It's going to tell me false. And the reason that it's false, even though it's true, is that, again, at some point in the line of decimal points, which it goes out to, we usually think about 20 or so, somewhere in those decimal points, somewhere there was a rounding issue and the decimal points did not match up the way they should have. And so you will absolutely end up with errors in your code because of it, and it happens in some silly ways, and it's just one of those things you just kind of have to be aware of, and, well, if it happens, try to figure out why. But we can use functions like round to try to make our lives a little bit easier. For example, if I tried to round each of these to, like, 2 or 3 decimal places, okay, they're going to match to the first couple of decimal places, and that might be good enough, or in a different case, well, maybe it wouldn't be good enough. So again, it's kind of case specific, but just something to be aware of when we work with numbers, and in particular decimals in programming. The next type of number is an integer, and your integers are your whole numbers. These can be positive or negative, but there's no decimal place after it. Now, when you store a whole number by default, R is going to, by default, store it as a double. So, for example, if I try to store the value 4 in my variable x, and then run my type of function to figure out what type of data type this actually is, it's going to return double. Because by default, R is going to store that as a numeric value. If you want to explicitly store something as an integer, you either put a capital L after the value, or you can use the function as.integer. And the as.dot function actually applies to a bunch of different data types too. But for example, in this case, I would do x, and I want to store 4. So now if we check if 4L, how that one is stored, well, now we run the type of function, and we see that now it's stored as an integer. All right, so again, if you want to, by default, store something as an integer, typically we put that capital L after it. The next data type is our logicals, and logical values have to be either true or false. And they are the results of our logical operators. These are also sometimes called Boolean. They are also related to binary, right? The ones and zeros, trues and falses. So again, if I want to kind of store this, so let's say I'm storing my variable x, I want to check, does 2 equal 3? And again, use the double equal sign. Well, does 2 equal 3? No, of course not. So what is stored in x? Well, the value false is stored in x. All right, and that is a logical. The last type is our complex, and complex data types store complex, or sometimes called imaginary or lateral numbers of that a plus bi form. So right, when we have that imaginary number I, they're really outside the scope of this particular course, but they are useful in a lot of mathematics. So for example, if I stored in x just the phrase 2 plus 3i and run the type of, it is automatically going to know that I am storing a complex variable here. All right, so those are our data types. Now we'll talk about our data structures, and data structures are how the computers organize and store multiple values in their memory. So the data structures can include the data values, relationships between the data, functions to be applied to the data. They can actually be fairly broad in scope, and it is important to make sure that we choose the correct function for data as we continue on in our data science careers and start doing more and more complex things, particularly if we want to get into data engineering or database design or those sorts of things, because it's very useful to consider what the data types will be and how our data is going to be used to create our data structures so that our computers can run as efficiently as possible. Because again, if you imagine a data set with, say, 1,000,000 values, and it takes 1 second to do an operation for every value, that's 1,000,000 seconds. And if it's stored improperly and it takes twice as long, well, 2,000,000 seconds is a lot longer than 1,000,000 seconds. And again, that's kind of a silly example, but that's the main idea, that, again, the way we store data so that we can retrieve it and use it does become much more important as we deal with bigger and bigger data sets, and again, we really try to engineer the way our data is structured. So our first data structure that we're going to look at is vectors. Now, vectors are one-dimensional data structures. Now, we're going to make the distinction that in our case, data in a vector must be homogeneous, and what that means is that we're only allowed to have one data type per our vector. Now, that means we sometimes call these atomic vectors, kind of like there's only one type of atom. So kind of like our data type is our atom, and then our data structures are our molecules that are made up of our atoms. And so vectors must only have one type of atom in them, and so again, they're kind of referred to as atomic vectors. So the nice part is, with our vectors, we store them, if we want, by doing C and then parentheses around it. And so I can store a vector of numbers like 1, 1, 2, 3, 5, or I can store a vector of characters like the names John and Diane. And what we can do when we store our vectors is we can use the type of function on the vector, and it's going to return the one single data type that is used. So for example, if I ran type of on my variable fib up there, it would tell me that they're all numeric. And if I were to run type of on my vector names, it would tell me character, because those are basically the atoms that make up that particular vector. Now, lists are one-dimensional data structures that can contain heterogeneous data types, which means that a list can contain multiple different types of data. Which means, for example, if I have a list called data, my list can store the character Liz, the number 1980, and the logical true. I can mix my data types up, and that will be fine. And if I run type of data now, it's going to tell me that this is a list, which is very nice. It's a list of data, which means it can have a bunch of different data types in it. Now, it's important to remember to use list if you want to create a list, or C and then the parentheses if you want to create a vector. If you accidentally use the vector function to create a list, R is going to use what's called coercion, and it's going to actually choose the most flexible data type to store everything. So if we take that last list, Liz, 1980, and true, if I wanted to store this and I accidentally store it as a vector now, right? If I use C parentheses to store it as a vector and I run type of, it's going to tell me that it's a character. And again, that's because, remember, vectors are only allowed to have one data type. And when we check type of on a vector, it's going to tell me that one data type. Now in this case, character is the most flexible data type that we can use. Basically, as we have Liz there. So it's going to store Liz as a character in quotes. It's going to store 1980 as a character in quotes, and it's going to store true as a character in quotes, even though we wanted 1980 to be a numeric value and we wanted true to be a logical value. So again, it's just very important to be very careful about how we store our data, and remembering, do we want a vector or a list for this particular application. All right. Next we have factors. So a factor is a vector that can only contain predefined values, typically for categorical data. Basically, we use it to categorize our data and store it in what are called levels. And again, they're very useful to categorize unique values. So if there's only a small set of values that everything can take on in my particular vector, I can create a factor, in fact, that's going to restrict me to those potential answers. So for example, let's say again, I'm using my variable x and I want to store the factor. My factor is now the vector that goes a, b, b, a. Kind of like the answer key to a multiple choice test, right? So I'm storing this factor, and again, I'm storing my factor as a vector with, again, specific values that must be unique. And if I run class, well, okay, the class of my variable x is a factor. And so class is kind of like the type of function where it is going to tell me, again, typically how my data is structured. So type of and class are the two main ones that we use. In this case, we use class as, the class is a factor, and the levels. So the levels are those unique categories, those unique things that that are allowed, the only ones that are allowed in that particular factor. So in this case, when I look at my levels of x, the only things that are allowed are going to be a's and b's. So those are my levels. Now again, my factor is stored. The a, b, b, a is stored. But the levels, there's only two levels. It can either be A or B. Those are my only two options. All right, my next data structure is the data frames, and we've been working with these a bit anyway. So data frames are the most common way of storing data in R because if we create them in a tidy way, data analysis becomes much easier. Now, what a data frame really is it's actually a list, but every element in that list is a vector itself. And each vector becomes the column of my data frame. So this means that all data frames must be two-dimensional, where again we have rows and columns. And again, we've talked about this before, but every column is my variable, and that means that each column can only have one data type. Because again, now my column, which is my variable, is now a vector, and my vector is only allowed to have one data type per vector, right? Now, the rows are observations. And again, those can have different data types. We've seen that already. You can have names and numbers and whatever else. But again, because these columns are all variables and they have to all match up in two dimensions, each column has got to be the same length when we make our data frame. Otherwise, we're going to run into errors. Next up, we also have matrices or a matrix. Now, a matrix is a two-dimensional array, and again, it's very similar to a data frame. It stores the data in that rectangular tabular form, where again, we have rows and columns. However, a matrix is a homogeneous data structure, which means it can only contain one data type, typically numeric. Usually, our matrices are just rectangular data of numbers, and again, become very, very useful for different types of linear algebra, and matrix arithmetic, and really important for machine learning. Now, matrices are a small subset of what are known as arrays, and arrays are data objects that can store data in more than two dimensions. You can have a three-dimensional array or even a five-dimensional array, and although it's very difficult to try to really picture how the data is structured in your head when you're talking about a five-dimensional array, the idea is, again, you kind of just scale up. So a three-dimensional array, so you would have a bunch of matrices, right? Two-dimensional matrices, and if you stack those two-dimensional matrices on top of each other, that becomes an array in 3 dimensions. And then if you were to stack three-dimensional arrays together, you get a fourth-dimensional array, and again, now we're at the point where we can really visualize what's going on. So, conclusion. Can we answer the following questions? So, what function or functions can I use to check the data type of a variable? If I wanted to store the year 2002 as an integer, how would I make sure that that is actually stored as an integer and not just as a numeric or a double? And lastly, what would the levels be for the following factor? Apple, banana, grape, and apple. Hopefully you can answer those questions. And, as always, take care of yourselves.